speaker. The title of the talk is Asymptotic Behavior of Prediction Markets. And our speaker is Philip Dawid. He's the Emeritus Professor of Statistics at the University of Cambridge. Hopefully needs little introduction. He's a fellow of the Royal Society, International Society for Bayesian Analysis, and an honorary lifetime member of the International Society for Bayesian Analysis. Excuse me. So we're very excited to have Philip here speaking about asymptotic behavior of prediction markets. Welcome.
Well, it's a great pleasure to be back at DIMACS. I was actually at a meeting in 2003, and it's nice to be back. The only difference is that last time I had to get on a plane to get there, and now I just have to make my way to my own sitting room, which is also nice. I'm going to talk about a very idealized version of prediction markets. It's by no means the whole story about general prediction markets. And what I'm doing is actually rehashing some material that appeared really, most of it quite a long time ago, in the economics literature. And it's been, together with Julian Mortera in Rome, we sort of rehashed that in a slightly more statistical framework, but there's nothing, we can't pretend to any great novelty in anything that we're going to say. So in terms of what it says sharing is paused. Sorry.
As far as I can tell, it's working.
Okay, it's working. I got a strange message. Okay, so our idea of a prediction market is we got a sequence of forecasts made by a sequence of individuals, individuals E1, E2, and they're going to make their forecasts sequentially, and they're looking ahead at some future event A, or in certain circumstances, it might be they're trying to forecast some continuous quantity. What happens is that each of these individuals has some private information. Individual E1 knows the value of a variable X1, and so on. For simplicity, and in fact it makes a difference, we assume that all individuals know which variables the others observe, so they know the source of their information, but what they don't know is the value of the information. Only individual EI knows the value, little xi, of his private variable xi. We're going to assume that they all start in a state of common knowledge. So if they all had the identical information, they would all have the same probability distribution over everything, but they don't have identical information, so they differ. They start off with a common distribution, and each then predicts in turn the value of A, coming up with a probability pi I, which so we have a trail of probabilities. So at each time, expert I, and the public at large can see all previously announced probabilities, but only individual EI knows his private knowledge, HI, which is the value xi equals little xi. So at time I, what does EI know? We'll call it TI. It's all the previous announced probabilities, pi 1 up to pi I minus 1, and his own personal private information, HI. Now, as I increases, HI will be replaced by pi I, and HI plus 1 will come in. But because pi I is generally less information than HI, pi I is the expert's forecast, which was a very meager summary of everything he knows. This is not an increasing set of information in time. But what's available to the public is the increasing sequence, pi 1 up to pi I, and you just keep adding to that as each new forecast comes in. Right, so what we're going to do is think about what happens to this sequence of forecasts as time increases and the individuals keep making forecasts. And there's only one piece of maths here, which is utterly trivial, but it's quite crucial. First of all, what is pi I? TI is the whole information available to expert I. That's all previous forecasts and his own private information. By definition, that's what he knows. So his forecast is his probability of A, conditional on what he knows. And the trivial lemma says that the probability of A given just the sequence, the trail of forecasts without the additional expert knowledge that I has is equal to what it would be if he had that expert knowledge. And it is indeed just what he says it is, pi I, and the proof is utterly trivial. I'm not even going to go through it. But the important point is that although the t's weren't increasing with time, the s's were. And what that means is we have a martingale. So we have a number of corollaries of that result. The first corollary is that if you're just looking at this from the outside, your information about A, given all the whole sequence pi 1 up to pi I, that's this, is just the last of the issued forecast. I'm not interested in any earlier ones. There's no, all the information is just in the last one. That's not, perhaps not very surprising. But what is a very important corollary of this result, because the S's are increasing, is that we actually have a bounded martingale. These are between 0 and 1, and this is the definition of well, it makes it a martingale. So the pi's form a martingale, and we have the martingale convergence theorem, which then says that there must be a limiting value, an almost sure limiting value as we throw in more and more experts, which we could call the consensus probability. As we go off to infinity, all the experts have said everything they've got to say, we get a consensus probability. That's what I mean by the consensus probability, the limiting value. One perhaps slightly surprising result is that this can't keep oscillating. You might think that new experts might keep on bringing in important, significant new information, and that these pi's could keep going up and down and never converging, but that's not true. Eventually, they have to converge. So it means that whatever new private information individuals bring in will necessarily be asymptotically negligible, which I found slightly surprising. Now, let's define this consensus value as the probability of A given the whole sequence. It's the limit of the pi's. And a very important question is that the same as what we would get if we merged all the private information that the individuals has? If they could actually get together and share their private information and pool it, they'd get a certain probability. Does this prediction market succeed in integrating all that? And in that case, we call the market having complete consensus. And the rest of this talk is basically giving you examples to show when this can happen, but it doesn't always happen. And I'm going to now restrict the story rather a lot. There's nothing that says these experts, these individuals have to be distinct people. They can be the same person coming back, playing over and over again. So let's have just two individuals, and they don't gain any new information. So they've always got the same information. E1 has always got information H1, the value of X1 equals little x1, similarly for E2. And they just keep playing in turn consecutively. So let's see when we might get various kinds of consensus. So let's suppose that the two variables they can each see, each one at a time, as the results of two independent coin tosses, X1 and X2. And the event that they're interested in is the event that they agree, that they both come up heads or they both come up tails. So that clearly has prior probability 0.5. What happens as they start to play? Well, as individual one looks at it, even though he knows the value of his own coin toss, it was heads, say, it's still a 50-50 chance that the second one will agree with his. So whatever he's bound to come up with his forecast as 0.5, which is therefore completely uninformative. There's no new knowledge obtained by learning that expert one says 0.5. So expert two, or individual two, has learned absolutely nothing. And by exactly the same argument, he says 0.5, and so on and so on and so on, ad infinitum. They converge, they have consensus on 0.5, but that's utterly vacuous. They've never learned anything. But if they could get together and pool their data and observe both coin tosses, they would learn the value of the result with certainty. Here's a similar example where they can't learn with certainty, but we have a bivariate normal distribution. So let's suppose that the two variables that they can observe are bivariate normal. Each one is standard normal, means 0, variance 1, but they're correlated. And what they're interested in is the correlation between x1 and x2. It's a variable, not an event, but they want to forecast it. They have some prior distribution for what this might be, but it's pretty obvious that each variable by itself is totally uninformative about the correlation between the two variables. So it's exactly the same story as within the two coin tosses. X1 is uninformative, so E1 doesn't update his distribution, and therefore there's no reason for E2 to update his distribution, and so on and so on. So once again, we have entirely vacuous consensus that they don't learn anything in the limit. They could learn something if they could observe both 1 and x2, although in this case, unlike the two coin tosses, they wouldn't learn with certainty the value of rho. They just have a single sample from the bivariate normal distribution, which would give some information about rho. And in general, it's very easy to show that we would get this vacuous consensus in just this case, when each one of these variables considered separately is independent of the event or quantity being forecasted, although there is information in the two taken together. Now, sometimes we can get complete consensus, which is to say it would be the same as if they shared their information. So here's one of many possible examples. Let's have a parameter theta, so we can think of it as an unknown bias of a coin, and it's got a prior distribution which is uniform on 0, 1. And we have 3 coin tosses with that probability theta of coming up 1, independent coin tosses. X1 and X2 are what our two experts are going to observe, and Y is a future value which they want to predict. So A is an indicator of whether the future toss will come up heads or not. Now, a trivial bit of Bayesian analysis shows that if individual E1 observes 0 or 1 heads, then he updates his distribution for theta, and therefore his prior it changes to his posterior. And as I say, trivial Bayesian analysis shows this, where that's either 1/3 or 2/3, depending as x1 is 0 or 1. But the important point is that there's a 1-to-1 correspondence between the value of pi1, it's 1/3 if x1 is 0, and 2/3 if x1 is 1. So when learning a pi1, expert 2, individual 2, has also learnt the value of x1. He can deconstruct it. So he's learnt x1, but he also knows x2. So now he has complete information, and from then on, nothing changes. They both have complete information, and we have indeed got convergence to complete consensus after only 1 round, and it never changes from then on. Another similar problem is with linear prediction. We have, just to be specific, 21 variables, mean 0. There's a specific, well, I won't tell you what it is, but specific known covariance matrix sigma. In E1 observes the first 11, E2, then from there the 12 to 20, and they want to predict the last one. And to go quickly through this, each one uses his best linear predictor based on what he knows so far. So U1 is best linear predictor based on X1, and if I tell you what the value of that is, I reveal the value of U1. And V1, now individual 2 knows what's just been revealed, and X2. And he reveals the value of V1, and we go on like this. And it turns out that after 20 combinations, after 10 rounds with 2 players playing, they have revealed 20 different linear combinations of these 20 variables. So it's not surprising that they've effectively revealed complete information, and they have complete consensus. There's a little numerical example where the forecast based on the full data will be that 39.7395, and the sequence of prediction goes, as they do keep learning as time goes on, they do keep learning, but they stop learning at time 10 when they in fact have learned everything there is to learn. They have got the full, complete consensus. We can also have limited consensus where they learn something but not everything. Suppose, again, perhaps the details of this aren't terribly exciting, but I'll go through it quite quickly. They have these variables independent normal one distributions, and x2 has a linear regression on x1, the regression coefficient is theta. And a little bit of statistical analysis tells us, well, pi 1, expert 1, he's got his information, he's got no information about theta at all. So nothing at all there. But expert 2, knowing x1, has got a linear regression problem, and he can learn about theta. And the sufficient statistic is actually the modulus of x2. So knowing what his posterior is actually reveals his value of the modulus of x2. And we go on putting that all together. And it turns out that eventually what they both end up knowing is the modulus of x1 and the modulus of x2. But that's not the same as knowing x1 and x2, and they have a limited consensus, and there's a random sign which gives you a mixture of the two full distributions. That's basically all I got to say. A lot of this work was done in the economics literature, some very interesting papers by Dutta and Polemarchus. One of the things they show is that if we play this game, it matters who makes the first move. So for example, it could be that if E1 makes the first move, then they get complete consensus. But if E2 makes the first move, then they get an incomplete, limited consensus. And there's also a rather mystifying phenomenon which they call obfuscation. Suppose that before the game starts, some independent referee makes some additional information publicly known to both experts. And therefore they continue, but having conditioned on that. And it can turn out that without the information, they could reach complete consensus, but with the additional information, it actually makes things worse, and they can lead to limited consensus. So that's, I think I've just about kept to my time, and that is all I have to say. There are some references. Thank you very much.
Thank you. Okay, so if you want to ask a question, please, to Professor David, please quickly throw it in. I'll try to fit one in really quick. This is possibly a slightly unfair question, but as someone who's very interested in these questions theoretically, I want to ask, should practitioners care? You know, so are these things we can cook up that are interesting in theory, or do you think we might see this happening?
Well, I think it is important in the sense, suppose you have the option, you've got various experts, and you want to get them to come to some sort, to provide some useful information on some future event. Is it more helpful to get them in a room and share their information on the one hand, or to go into a prediction market where they come sequentially? And I think the story here is it's better to get them together in the room.
Great. Yeah, nice callback to good judgment, of course. So I'm not seeing questions come up, and I think unfortunately for time, I have to cut them there. Thank you very much. Really appreciate the talk.